Welcome to The Explainer. Today, we're totally tearing down the myth of the blue planet. You know, from space, Earth looks like this infinite, beautiful marble of water. But when you actually dig into the hard math behind global water scarcity, a really different, honestly urgent picture emerges. Our natural water supply is quite literally caught in a vice right now between severe environmental threats and explosive human demand. But hey, don't worry, it's not all doom and gloom. We're also going to look at some of the truly fascinating engineering that's stepping up to solve this.
Here's our roadmap for today. We'll start by unpacking the blue planet paradox, then look at the biggest threats to our water supply and the reasons behind our surging demand. After that, we'll dive into how we're engineering new sources, look at a very real case study with the Karachi crisis, and finally, talk about conserving our future.
Section 1. The Blue Planet Paradox. Let's dive right in and look at the massive gap between the water Earth holds and the water we can actually use.
Okay, so you've definitely heard the stat that Earth's surface is 70% water. But there's a massive trap hidden in that number. A whopping 97% of all the water on Earth is locked up in our seas and oceans as salt water. And that salt water is completely useless for agriculture. The high salinity literally destroys soil and plant cells. And obviously you can't drink it without experiencing severe dehydration.
So, doing the math, that leaves us with just 3% of the world's water as freshwater. But hold on, it gets tighter. 79% of that freshwater is frozen solid in ice caps and glaciers. Another 20% is buried deep, deep underground, often way too far down or just too expensive to practically pump out. The absolutely crucial takeaway here is this. Only 1% of the world's freshwater is easily accessible to us on the surface, in rivers, streams, and lakes. Just 1% of 3% is sustaining pretty much all terrestrial life on Earth.
Section 2. Threats to water supply. That tiny, precious 1% we just talked about, it is under some incredibly severe pressure right now.
We are dealing with two fundamentally different, but equally destructive, human footprint issues that are aggressively disrupting the natural water cycle. On one hand, you have parched desertification. In places like Madagascar, for instance, clearing forests has led straight to desertification, which means less rain is returning to the ecosystem. On the other hand, you have urban sprawl. By paving over natural landscapes with massive concrete cities, we're blocking whatever rainwater we do get from seeping back into the earth to replenish our underground aquifers.
Basically, how we use our land dictates our water survival. Think of a natural forest like a giant sponge. It soaks up rainwater, holds the soil together, and crucially, it adds humidity back into the atmosphere through evapotranspiration. That's a really cool process where trees literally sweat water vapor from their leaves, which then fuels cloud formation and brings more rain. Urban sprawl does the exact opposite. Concrete completely blocks that infiltration. Instead, you get rapid runoff that triggers flash floods and sweeps all sorts of heavy metals and chemicals straight into our rivers.
And beyond land use, we have climate change driving higher temperatures, which speeds up soil evaporation and causes these really erratic swings between severe droughts and extreme floods. Then, of course, there's pollution. With 6 billion people producing waste on this planet, our clean water supply is shrinking fast. Industrial air pollution causes acid rain, and agricultural fertilizers are constantly washing into lakes, causing toxic algae blooms. These blooms literally choke the oxygen out of the water, poisoning that fragile 1% of surface water we so desperately rely on.
Section 3. Reasons for surging demand. Now let's look at the other side of this global squeeze. While our usable supply is shrinking, our demand is skyrocketing.
The drivers behind this demand surge are just staggering. First up is population and urbanization. Back in 1900, the urban population was just 13%. By 2030, it's expected to hit 60%. And people in cities don't just drink water, they're watering lawns, washing cars, running appliances. Speaking of which, electricity requires massive volumes of water just to cool power plant engines and spin hydroelectric turbines. But the real jaw-dropper here? Agriculture. A staggering 69% of all fresh water is used strictly for food cultivation. We are literally draining underground wells dry just to keep food on our plates.
Section 4. Engineering new water sources. I know all of this sounds pretty grim, but this is where human ingenuity comes in. We are stepping up in some major ways to artificially expand our water supply.
Our first line of defense is just being incredibly smart about what we already have, through meticulously managed water catchment areas. Take Singapore, for example. It's a land-scarce country with no natural lakes or massive aquifers. So they've taken optimization to the extreme. They've engineered these extensive networks of canals and rivers to capture rainwater and paired that with super strict soil erosion and solid waste management. It basically ensures that almost every single drop of rain that falls on the island gets channeled cleanly into a reservoir.
Now, to really scale up our supply, engineers have finally started tapping into that otherwise unusable 97%, the ocean. Massive desalination plants, like the ones you'll see in places like Perth, Australia, are removing the salt from seawater to create fresh, drinkable water. We've used this on ships for decades, sure, but scaling it up to sustain entire major cities? That is a total game changer. The catch, though, is that it requires highly expensive infrastructure and a massive amount of electricity. We generally pull this off using two main methods. The first is distillation. This is where we use huge amounts of heat to evaporate seawater into vapor, leaving the salt behind and then condensing it back into liquid freshwater. The second is membrane filtration. This involves forcibly pushing water molecules through a semi-permeable membrane that physically traps the salt. Membrane filtration does use a bit less energy than heating, but the financial cost for both is still a huge hurdle. Those delicate membranes require constant maintenance and replacing, which honestly prices out a lot of developing nations.
Then we have another incredible engineering feat, water reclamation. Yes, this means taking used wastewater straight out of the sewers and purifying it. It's actually been used in Europe and the USA for over 20 years to take the pressure off freshwater supplies. This reclaimed water can be used for factory cooling, agriculture, or purified all the way back to perfectly safe, potable drinking standards. And as a quick kind of mind-blowing aside, scientists are even experimenting with cloud seeding. They are literally dispersing particles like silver iodide into the air to give water vapor something to condense around, artificially forcing it to rain in dry regions.
Section 5. The Karachi Water Crisis. To really grasp the gravity of everything we've just talked about, let's zoom in on a micro case study and ground these big global concepts in the reality of one specific city in Pakistan.
16 million. Think about that number for a second. That is the baseline population of Karachi struggling for reliable hydration today. It's Pakistan's financial capital and truly one of the most populous cities in the entire world.
But then you look at the growth projections. The population was projected to hit 28 million by 2020. This explosive mix of rapid industrialization and mass migration into the city means that every 2 years, Karachi's water demand increases by an additional 120 million gallons per day.
So that brings their current daily demand to 600 million gallons. That is what's required every single day just to keep Karachi functioning. And the craziest part, 500 million of those gallons have to be drawn from the Indus River, which is a full 150 kilometers away.
To prevent a total collapse of the system, the city government proposed an absolutely epic feat of engineering called the K4 Water Supply Project. It's a $270 million proposal to literally double their water capacity, and involves building 4 massive 150-kilometer channels drawing from the Indus. But here is the really genius part. They designed the routes to utilize the natural gravitational pull of the landscape to move the water, which saves a massive amount of energy. But when you drastically increase the city's water supply, you also have to manage a massive increase in wastewater. So you have to factor in 2 new treatment plants and a staggering $9 billion parallel sewage project called S3. It really puts into perspective the astronomical price tags attached to out-engineering water scarcity.
Section 6. Conserving our future. Because while these multi-billion-dollar engineering projects are absolutely vital, they aren't a magic fix. We have to bring the focus back to everyday responsibility.
As the source material reminds us, ensuring resources are used carefully is quite literally everybody's business. This means we need a dual approach. First up, education. We need to get into schools and teach children good stewardship so the next generation inherently respects this resource. Second, we need technology at the consumer level. That means fitting homes with water-saving gadgets for taps and toilets, and fundamentally upgrading how we farm. We have to replace highly wasteful flood or spray methods with advanced drip irrigation, which delivers targeted water straight to a plant's roots. That alone drastically cuts the agricultural drain.
So I want to leave you with this final thought. We started today by tearing down the illusion of the blue planet. Knowing now that only 1% of the world's freshwater is actually readily available to us, how does your daily footprint fit into this delicate balance? Every time you turn on a tap, water your lawn, or even just leave a light on, you are pulling from that 1%. The math is undeniable, but finding the solution starts with understanding the reality of it. Thank you so much for joining me on this explainer, and keep learning.